Welcome back. The second speaker is Professor Yishuai from Binza. The topic of this lecture is difference of sums of square decomposition for polynomial. Let's welcome.
Thank you for presentation. And ladies and gentlemen, welcome you to my talk. And after the heavy rain yesterday, I'm very happy to meet you again here. And the temperature is cooled down, and I hope this lecture will warm you up. So today I will talk about polynomial decomposition techniques. You know the polynomial decomposition is something long history, okay? And particularly the decomposition technique based on sum of squares can come back to the 1880s, the age of 1880s from the David Hilbert, and related to the famous Hilbert 17th problem. So today we will present a new type of decomposition technique based on some square, namely difference of sum of square decompositions. Okay, this is recently developed by several papers, and which will pave a new way to get a better understanding of the algebraic structure of polynomial. So let's start. So firstly, I will talk about the problem and the motivation, then get a very quick review about the development of sum of square decomposition for polynomials, then focusing on the new type of decomposition, the difference of sum of square, and the difference of convex sum of square. If the square are still convex, that's a particular special case and very useful case in practice. And the last, I will talk about some interesting open questions. So first, about the problem. So the problem is that given any type of multivariate polynomial of any finite degree, we want to know, can we rewrite them as difference of some sum square polynomials? Or if the polynomial are convex, the squares are convex, so that's a special type, difference of convex sum square polynomials. So this is the question. And formally, so we can define the problem using two square polynomial s1 and s2. So we make the difference to get the decomposition of any polynomial p. Okay. And the definition and the property are started in our recent paper published on some journal optimization. And here I will not cover all of them, but give you some major results and some decomposition algorithms. So let's first talk about the motivation and the theoretical value. So we have theoretical value and a practical value. So in theoretical aspect, so it is very important to get a better understanding of the inherent fundamental structure of polynomials. So the story is like that in 1886, around that. So the Minkowski proposed a question, is every non-negative polynomial is indeed a sum of square of some other polynomials. So this is proposed as a bold conjecture of Minkowski during his PhD defense. And David Hilbert is one of his examiner, and he's convinced that yes, maybe there indeed exists some special case that a non-negative polynomial cannot write like a sum square, but he cannot find any example. Okay, and after 3 years, so David prove negatively, but in a non-constructive way, that the answer is no. Okay, despite that he cannot provide any example, but he provide it in a non-constructive way. But this is just the starting of the question, and after that, this question leading to the famous Hilbert 17th problem, meaning that a non-negative polynomial cannot write as a sum square, but maybe it can be written as a sum of some rational functions, meaning sum of some squares over squares, something like that. And okay, so after 20 years, more than 20 years, so Emil Attin give the right answer. Okay, it is correct, and so the question is over. But it's not meaning that this question is over, but not mean that the research is over. In fact, it's just the starting of the story. And firstly, the proof of our team grounded the basic of the real algebra, and these ideas open some new chapters in many branches of mathematics, such as real algebraic geometry and many theorem studies in positive polynomials, and leading to the modern polynomial optimization field. Okay. So in today, we are studying the first question a little bit further about the extension of this question in difference-of-sums-of-squares, because non-negative is just a special case of polynomial. But polynomial is not always non-negative. It can be take positive and negative value. So in practice, given any polynomial, either positive or negative, or both of them, so can it still be presented using some square structure? So the idea is that maybe we can just make the difference. Okay? So the question is that can we write any polynomial, any degree as a difference of square, or even the square is convex? And the answer to this question is yes, and provided by us in our recent study. And this leads to a new, deeper understanding about the polynomial structure. So another very important part is about optimization theory. Okay, so the sum-of-square decomposition have a very close relationship to optimization, and particularly to the special question. It is called a convex optimization problem, semi-definite program. So it's formally defined like this. So here the AI from 0 to n are some linear mappings. Okay, it's take a variable, is a matrix variable, n times n, and return to some real values. It's a linear function. Okay, and we can define the problem like minimizing a linear function over some linear constraints, okay, equality constraints, and with variable, the matrix variable is defined to be real, symmetric, positive semi-definite. Okay, meaning that all eigenvalues could be either strictly positive or zero. Right? And I will say that sum-square decomposition can be checked in polynomial time by solving an STP like this. And for D-SOS and DC-SOS, so we can also extend the result, meaning that we can construct the corresponding STP problem and solving them to guarantee that any polynomial can have such kind of decomposition. Okay, so this is the first important part about optimization theory. The second is that also the question about our initial motivation when we started this kind of problem, because it will establish the bridge between polynomial decomposition and polynomial optimization with a branch of optimization we call the difference-of-convex optimization. Because once we rewrite the polynomial as a difference to convex polynomial, then it's kind of we said DC function. And there are many people who are studying this kind of problem, for example, Professor Yuan as well. And so there are many interesting techniques to solving this kind of problem in an efficient way, especially for large-scale optimization. Okay, so this is our initial motivation to study this problem, and also based on this, we have a lot of applications because many application problem can be formulated in this way. So the polynomial optimization, so is here we started to minimize some polynomial function fx. So for x be an n-dimensional variable. And indeed, in theory, we know that it is equivalent to a special case of DC, meaning difference-convex optimization, minimizing a DC function is a difference of two, g and h are both convex functions. Okay, we can say that. Of course, the definition is formal definition more complicated. So the convex function should be proper, closed, or something else. But practically speaking, you can understand that it's just some kind, for example, real valued convex function is okay. But in fact, this convex function can take some infinity value, okay, part infinity on some part, okay. So, as a result, so any polynomial optimization is a special case of DC function, as the function is differentiable, okay, and infinitely differentiable for G and H. And but the question is that how to write any polynomial as DC. So for a long time it's still an open question, but right now it's no longer open question based on our study, because we can use D-SOS and all DC-SOS decomposition techniques as a very robust way to generate infinitely how many decompositions. Okay. So here I give you a short example, very trivial one, a quadratic case to make you understanding why a polynomial can be right hand DC and where is the squares. For example, here I define the function fx as a quadratic form. So the matrix Q is a real symmetric matrix, but the eigenvalue could be negative. So there are three typical classical DC decompositions. The first called projective DC decomposition. So it's just to find some large enough parameter mu such that the part G, okay, the first convex component is a square, and the rest of the part is not necessary to be square. So here we can use the square to get a decomposition. It's a DC. If mu, for example, larger than the largest eigenvalue of the matrix Q, and of course, if it's a negative, we should take that. Okay. And the second is the proximal DC decomposition. It's just to exchange the row of G and H. We take H to be the square, and if mu is large enough, we have DC. In G and H are both convex. And the most interesting part is that we have what we call the spectral DC decomposition. It's based on a spectral decomposition of the quadratic matrix Q, like we write and P lambda P transpose, and lambda consists is a diagonal matrix consists of all eigenvalues. So we can write it like lambda plus and lambda minus. So lambda plus consists of all positive, no negative eigenvalues, and the lambda minus negative ones. Okay, and like this, so we can rewrite f x, the quadratic form, as the part G and minus part H. And the part, both of them are in fact, if we replacing the matrix Q as P lambda P transpose, so we can see that it's exactly sum of squares. Okay, so G minus H should be the difference of two sum of squares. So we have difference of D-SOS decomposition for a quadratic form. So the question is that, of course, this is a well-known decomposition. Okay, the spectral decomposition. Can we extend this result to any polynomial, any degree at any variables? So this is the focus of our work. And last but not least, about the motivation. So based on the decomposition and the connection with DC, and you know the wide range of applications in optimization with DC structure. So we have many real-world applications, including some of them, but not all of them. Okay, data science, machine learning. For example, recently we have CAN neural network, common log alpha node neural network is based on split and polynomials. We can using our decomposition to explore the special structure of this CAN network, and we can do something better, for example. Okay, and matrix analysis, semantic science, image processing, optimal control, and many of that. So some of them we have also related publications, and many other authors have some publications, and some of them are still new. So if you have interesting, you can read them, okay, from the internet and do some studies. So now I will come to the second part, polynomial decomposition based on sum of square. Very quick review about, I give some based on some formal definitions. The first is we use this abbreviation, this notation Rx for the vector space of real valued polynomials. So variable x belongs to Rn. The coefficients are real coefficients. Okay, and with this d, meaning that the degree of the polynomials up to d could be smaller than d or equal to d. Okay, and sum of square polynomial, so just like the name of the definition, so it means that a polynomial can be written as sum of squares of some other polynomials. Okay, and a very close related definition is called the PSD polynomial, non-negative polynomial or positive semi-definite polynomial, meaning that the polynomial is defined non-negative over the whole space Rn. Okay. So as I said, the Minkowski's the proposal question between the equivalence of two sets, and the answer is provided by Hilbert. That answer is false. Okay, we just have one direct inclusion. Sum of square is of course negative, but reversely, it's not true. And Hilbert proves that there are only 3 cases that we have equivalence. The first is just a one variable, univariate case. Second, the quadratic case, like the example I have shown you as in the previous slide. And the third case is for 2 variables and the degree equal to 4. Okay, and in all other cases, Hilbert said that it is always exists some counterexamples, but haven't found any example. Just after 70 years later, okay, and Moskvin proposed a first counterexample, but not for this problem. It's just coincidentally for other purpose, but after that, it is recognized by Tosky and Todd that it is exactly the missing pieces that they want to find. It is an example given in formulation 1. Okay, if we draw the example, you can see that it's just like this. We have 2 variables, and we can draw the 3D picture. So the 0 is just the black line below. So the polynomial defined non-negative, but it cannot be written as a sum of squares. It's based on the geometric and arithmetic mean, and you can prove it. Okay. And about the complexity, so we can find that the PSD non-negative polynomial is NP complex. There exists some examples that checking this polynomial to be non-negative is NP hard. And but sum of square is something very beautiful because it can be checked in polynomial time by solving the SCP in some interpolation method. Okay, so next about some more properties. So we know the sum of square, in fact, is a convex con. Okay, but here we want to study some extension of sum square with convexity. So we can show that it's still a convex con. It's a proper con. And we also show that there is a relationship between the well-known SOS convex polynomial proposed by Hilton in 2010, but it's different. Okay, so this SOS convex means that a polynomial whose Hessian matrix is a polynomial matrix can be written as another polynomial matrix M transpose times M. Okay, so clearly meaning that the Hessian matrix is known is the PSD matrix, positive semi-definite. So the polynomial is convex, but of course it's not equivalent to the convex polynomials. SOS convex is not equivalent to convex. That is proved by AAA Hamid in Princeton University. But here, what I want to say is that if a polynomial is convex, sum square is not equivalent to SOS convex. Because SOS convex just meaning that the Hessian matrix is non-negative definite, but not meaning that the polynomial is square. Okay, and here are some relationship between that. So we have C-SOS is a polynomial that is convex and sum square, and SOS convex is just a Hessian matrix is a positive semi-definite. And you can see that there are relationship. Okay, so there's a special case it's a non-negative and SOS convex, which belongs to both of them, but they are not equivalent. Okay, so here in this graph, all inclusions are strict. Okay, the reverse is not true. They are always a counterexamples. Here, for example, the Hamidi provides this counterexample, meaning that sum of SOS convex, it belongs to convex, but they are not the same. And the same example serve as a counterexample for this inclusion. Okay, because this SOS convex is not equivalent to C-SOS. Okay, and of course here what we are interested in is that the polynomial that is both sum of square and SOS convex, because in this case we can check in polynomial time. So here are some complexity results. So checking the SOS matrix and SOS convexity can be done in polynomial time based on the property of algebra. Okay, but checking a convexity for a polynomial, for example, degree up to 4, once it higher than 4, there are some example in degree 4 that is NP-hard. And checking C-SOS in general is NP-hard based on this convexity, okay, based on this case. But checking the intersection of them can be done in polynomial time. And that's something tractable case. And based on which we establish our theory. So now we focusing on our new decomposition techniques, difference-of-convex-sums-of-SOS and difference-convex-SOS. So here is the definition. So we use this notation with n or nd, n meaning n variables, okay? It's a set of polynomials in Rn, Rx, and nd meaning that the subset in Rdx, okay? And first we can show that these two sets of polynomials are vector space. Okay, so we have one inclusion. So D-SOS or DC-SOS belongs to Rx or Rdx. But the reverse is not trivial. And in theorem 3, we prove that in fact they are exactly equivalent. Any polynomial, So any polynomial can be written as a difference-of-convex-sums-of-squares and a difference-of-convex-sums-of-squares. So the two sets are equivalent. So this establishes the representability of D-SOS, DC-SOS. And further, we also show that the degree of each component, because we have square component, okay, the degree is not smaller than this one. Okay, this meaning that if the degree of P, the polynomial, is even degree, so it's exactly the same degree. Okay, but if it's odd, it's just the degree of P plus 1, because it's square. Square should be even, right? So this is the second. The third is that it's not only not smaller than this, and there exists the decomposition whose maximum degree exactly equal to this one. So we can obtain the optimal decomposition. So that is representability. And about complexity, so we show that both of them can be constructed in polynomial time for any desired position, because it's equivalent to some kind of S. Okay. So I will not show the details, because this is the major result I've chosen for you. And after that, I want to more focusing on, based on, we know we can have some decomposition, how to construct them without solving STP. So STP is something very difficult to solve. Even in theory, you know, there is some method to get the solution. But question that if the STP is very large here, as we have no particular structure, sparsity of low rank to be employed, solving some kind of problem is very difficult, okay, time consuming, and even intractable. So in practice, we need some more practical method and efficient. For example, without using some parallelizing, okay, so efficient construct of a kind of decomposition for using practice. And that is what we want to present in the next slide. So the first practical decomposition method for D-SOS, we call the spectral decomposition. It's an extension of the spectral decomposition for quadratic form. Here we extend to the more general polynomials. So here, the first definition is about a valid basis. So valid basis is a kind of a polynomial vector. We denote as B, such that there exists a real symmetric matrix Q called grid matrix. So here B is dependent on X, Q is not dependent on X. Okay, such that for nx, the P is equal to the B transpose QB. Okay, so if for some b can such that we can find some q to get this equivalent, then this b is called a valid basis. That's why we make it valid. Okay, it's a basis and it's valid. So there are some examples. Here is the example of two variables, x1 and x2. So the valid basis is not unique. So you see we can have some b like that and q like that, or b like that and q like that. Okay, the degree of them are not the same. Here the degree is 3, here the degree is 2. We can have many valid bases. But once we get the valid basis, so we can use them to construct the decomposition. Because given b for p, okay, and we can find the matrix q by solving a linear system. So here's the linear system, because two polynomials cross if and only if all coefficients are cross. So this meaning that we have a system linear equations about the variables in Q. Okay, so we can solve that. Of course, the solution may not be unique, right? And for any matrix Q as a solution of the system, so we can find it eigenvalue decomposition, and based on which, so any polynomial P can be written like this. So it's a vector if P transpose B denote as a vector Y, okay? And the lambda is the diagonal matrix with eigenvalues. So meaning that P can be written as difference-of-convex-sums-of-squares. Why difference? Because lambda can be either positive or negative, right? It's eigenvalues. So you see, we can easily construct such kind of special decomposition for any polynomial with a given basis matrix. And in this way, if we find a decomposition like this, we can show that the maximal degree for the sum-of-square component is up to twice of degree of bx. So the degree of bx is very important. We want to find some decomposition with lower degree. Okay, so this is an important and interesting questions to be investigated. How to find a basis is valid. Second, how to make it the degree as small as possible. So here are two trivial decomposition, what called direct basis decomposition and minimal basis. Direct basis is easy, but the degree is not optimal. Minimal basis is optimal degree decomposition. Okay, the first direct basis is very trivial. So the direct basis is defined like a polynomial P. We write as sum of some monomials. So if we collect all monomials into the one side V, and if there is no constant part, we add y, then this is the basis. Okay, why this is basis? Because here's the example. If 5, here is the constant part. If we have 1, x1, x2, this is just one monomial, and with the constant 2 monomials. And here we have x1 squared, and with 1, because we have no constant part, right? And why is basis? Because you can just write the grid matrix like this. Just only the first row and fourth column are non-zeros. And this matrix have only 2 different, possibly non-zero eigenvalues, and we can compute it precisely and with the corresponding eigenvalues, latent eigenvectors. So the decomposition is just like one term minus another term. Okay, just have one term for each square. Okay, so it's the minimal size of squares decomposition, but not a minimal degree one, because we can prove that the degree is up to twice of the degree of P, not something we like. But it's very easy to have a such kind of decomposition. If you're, for example, in optimization, if the degree is not too high and this kind of decomposition, this kind of polynomial can be easily solved in practice, this provides you some intrinsic algorithm. Okay, so this is the first one, and that is example for the first one. So we start from this example to get the corresponding basis and matrix, and finding the eigenvalue 3 and minus 1. So we get the trivial decomposition. Okay, and of course it's easy, but not very interesting. We need some more refined way, especially for degree should be decreased, because a higher degree polynomial is not stable and also difficult to be optimized. So here is a minimal basis decomposition based on the definition called minimal basis. It's kind of basis whose degree up to half of the degree of the total polynomial. Okay, so in this case, you can find that of course the minimal basis is always exists but not unique. Here's an example. If we collect all monomials of degree up to the half of the degree, then this is trivially a minimal basis, right? And any polynomial of degree D can be written using this, right? But it's not the shortest one. In practice, there are a lot of shortest ones. For example, x1 squared, you can just use x1 as the shortest minimal basis. You do not need to illustrate all monomials of degree up to 1, right? And here is an example for degree up to 3. Okay, you can just have 2 elements instead of 9 of them, right? So this is what I want to see. So always exists some minimal basis and not unique, and we are going to find the shortest one. And here is a way to generate a minimal basis with a length as short as possible. So here the idea is that we get monomial by monomial m. So the OM is just the level of the corresponding variable whose degree is odd. Okay? And if the set is empty, then we can just have one element for this minimal basis. And otherwise, so we will separate all into 2 distinct parts, O1 and O2, and the size of them should be, the difference of them should be up to 1. It means either equal size, or one is one element more than another one. Okay, and in this case, so the minimal basis set is just 2 elements constructed. Okay. And union them, we will get the minimal basis for the whole polynomial P. Okay, and based on which we propose the minimal basis special decomposition. And theoretically, we can prove the degree is up. Right. So that is an example. I think it's trivial. I will go through very quickly. So we get some minimal basis first, Bx, using the procedure presented, and finding the matrix Q by solving the linear system. And so you see the solution is very sparse. So it's in practice, very efficient to be solved, even the scale is very large. And after we find the special decomposition for Q, and based on the step 3 of the previous algorithms, we can find the decomposition S1 and S2. And so they are sum-of-squares. Okay? And the degree is optimal. Degree is 4. Exactly for the twice of the half of the degree of P. Right? So the intrinsic property about this kind of decomposition is undomination. So undomination meaning that a polynomial, if it has a decomposition S1 minus 2, is undominated, meaning that there is no other square polynomial S such that both of S1 minus S and S2 minus S are sum-of-squares. Either of them should not be sum-of-squares. Okay? So it means that it's kind of optimal decomposition based on in the sense of domination. Okay. So and we can show that minimal basis special decomposition is exactly undominated is the best one. Okay. So and this provides a generalization of the special decomposition from the quadratic case to the any degree polynomials. So that is about the D-SOS. And the first decomposition. This is the second decomposition about parity decomposition. That should be some kind of decomposition more easy to be understood without eigenvalues. And the idea is that we can factorize any monomial x power alpha into 2 parts, O and E squared. O compose only all the degree variables, like x1 or x1 cube, something like that. Okay, and E squared are only even degree parts. Okay, for example, x1, 2, x2, 3, so you can get xo as x2, and E squared as the left part, or O as the x2 squared as 2 cube, and the left part as square. Okay, and in this way, if we can find a difference of sum of square for O, multiplying by another square, so it's a decomposition, right? It's a very trivial case, but very easy to be implemented. So, and in this way, you can show that the degree is the maximum of the degree of part O1, O2 plus twice of the degree of E. So if you want to get a minimal degree, so you should find a good decomposition O and E square such that the sum is minimized. Okay. So, and here we have two techniques. The first is the parameterized parity decomposition, meaning that if you get a factorization O E square, and to get the decomposition of part O, you can just plus x square minus square of them, sum of square of them, right? So this is a trivial case. It's parameterized because the parameter plays an important role to the quality of the decomposition. Okay. But it's very trivial to be established. And the theorem theoretically can show that the degree is degree of m plus degree of O, meaning that if you want to minimize this degree, you should minimize the degree of O, or find the O whose degree is as small as possible, right? And based on this, how to get a minimal degree O, you just need to choose all the degree variables just once, right? If x1 cube, you just take x1, right? And so you get a minimal one. So so here I think we do not need to see this example because it's very trivial, and you can get the improved one, meaning that the O part is just the multiplication of xi for I in set O. And in this way, to get the decomposition of OX, you can make couples of elements in O, so either xi, xg, or xi with 1, right? And each of them has a D-SOS decomposition, and multiply them and get the final result. Okay, so this is like it. And can show that this is exactly prove the optimal degree decomposition. And here's the example to show how to do it. For example, this O, this monomial, so the O part is 1 and 2, so x1, x2 are both even O degree variable. So we can, O is just x1 times x2, and the rest of part is E, right? And O, so this is trivially can be written difference of convex like that. So multiply square to get the decomposition, and the degree is optimal. Okay, so if one monomial can be written like this, so any polynomial can be written like this, just repeating all monomial, meaning that this method can be parallelized. Okay, you can take a monomial binomial to get the decomposition and the sum of them. Here are numerical results experiment for different sum of square without convexity. So here are two boxes. The one box for decomposition, another for polynomial modeling, and both of them we have provided the open source. And here we test a set of 1,750 polynomials generated with coefficients in this interval, and the number of variables from some very small cases, 2 variables to 20, because most of the applications there are 20 variables, up to 20 variables, and the degree up to 6. In most of the applications we cannot handle very high degree, so degree is equal to 6. Try to cover many applications in practice, and the density from very sparsity, 20% to some 100% sparsity. Okay. So and each setting we generate 10 polynomials and make a collection of 1,750. So here is the combination of this method. You can see that here are two sets. The first set is IP DSS and the PP DSS corresponding to parity decomposition, and the rest corresponding to special decomposition. Okay, so you can see that here we change the size of the polynomial n, degree d, and the density. So you can see that all of them are very similar. Okay, of course it increase with the increase of size and degree and density, but not very quickly. Okay, not very quickly. The second that you can see that this is for the last graph. This is the maximum degree. So they are provide different quality decompositions, and the average. So the best average is obtained by IP. Okay, and the minimal basis, right? So and with a small deviation as well. So you can see that the best is in fact provided by MBS, a minimal basis decomposition, and who provides the minimal degree with smallest average and within the shortest time. So this should be the best one among the others. And here is a parallel test. We use 60 processors, and for the case IP, D-SOS, and PP, because these are decomposition monomer by monomer, so we can parallelize that. And we show that there are 4 for the maximal speed up for the first one, and with around 15 processors. Okay, but there's no speed up in PP. So again, it's it depends. Okay, or even we use more than 15 processors, but not meaning that all these processors can make a contribution to the speed up. So 15 is already in the optimal one for IP, but PP unfortunately have no speed up. Okay, that is what I said. So now I will end 15, right? Okay. Okay. So the second part about decomposition with convexity, this is the more intriguing part because we need convexity in optimization. Okay, a polynomial just a sum of square is difficult to optimize. But a polynomial, if the polynomial is convex, we can, based on the robust theorem in convex optimization algorithm, to get some efficient algorithm in practice. So the first idea is based on the parity decomposition, based on the elementary 3 elementary cases for any monomial x power alpha. So it can be factorized as either multiplication of 2 single variables, or xi power even degree, or the multiplication of 2 difference-of-convex-sums-of-squares. And in fact, all of them can get some trivial decomposition. Okay, so you can just multiply them in an intelligent way to get a minimal degree of decomposition based on parity. So here is just a general framework in that for a monomial, if we factorize a part x power alpha, and we into elementary cases, and using this sequence of after A to C, you can produce a decomposition for x power alpha and multiply the coefficient to get the decomposition. And but in practice, there are some questions. For example, how to get factorized alpha, and how to apply A to C in a right way. So they are corresponding to what we call improved parity, meaning that it can get the best degree decomposition possible in this way. So here, I haven't presented the details, but you can write in our paper that we propose 2 procedures for factorize x power alpha and define the order of multiplications. Then we can get the best degree like this. You cannot get better than this one. Okay, meaning that here the degree, once degree of m is larger than 2, you can just get the 2 to power of the logarithm of this one. It's not the exact degree of m. Okay, it's equal to if degree of m is a power of 2. In other cases, there's a gap. So it cannot achieve the really best decomposition, except for particular cases. And here's the example for degree of 3. So we can factorize x power alpha as a couple of this, x1 with 1, x2 with 2, x2, right? And using A to C in this order, so x1 with 1 to apply the formulation A to get this, and x power is already even degree, so we can add a trivial decomposition and apply the multiplication of 2 decomposition using the formulation 3C, and you can get the final result. Okay, this is a very trivial case, and if any monomial can do it, so any polynomial can do it as well. But this may not be the minimal degree. Here is a special case because we have minimal degree 4. But if you get an example, for example, x1, 2, x2, 3, in this way, you cannot get it, okay, because based on this, And here, how to get a minimal degree? So you cannot use imperative one. Imperative one has some limitation, even despite it's very easy. Okay, but here we propose it's called the minimal degree one. It's based on this K identity. So in this identity, you can see that it's true for any m, integer m and n. And you see that the left side is the sum of some homogeneous monomials. And the right hand side is the sum of linear power of linear forms, the sum of x, xg, okay, of power m. So you see there is the equivalence between them. And based on this very interesting identity, and we also establish the multiplication if we replace each xi as a convex sum square. Okay, pi, then the multiplication of pi, just the left part, is equal to the right part. And the right part, in this case, exactly difference of sum square. And we prove that this leading to a best degree decomposition. Okay. And you may doubt that maybe there are there's a lot of subset. But in fact, in practice, this is not the case. As an example here, if we think about this polynomial, okay, a monomial, and we factorize first in elementary cases in step 2, and each of them can have some decomposition using A to C. Here, just A to A and B, not C, because C will replace by this formulation. So the multiplication of each term, Gi, Hg, okay, we need to multiply of them is multiply of the cross multiplication, okay, Gi or Gg or Gi, Hg, okay, and you see that there are the only two non-zero terms, this one and this one, and both of them can apply this formulation to get a very short decomposition. So this leading to the final result. Okay, it's not as long or as complicated as you see. And you finally, after the rearranging the terms, you have twice of the sum of them and twice of sum of them for the left part and for the right part. And the degree is optimal. So this is based on the very interesting identity to get some decomposition. The last one is called the power sum DC-SOS decomposition. It's based on a very interesting matrix we call power product matrix. It's DNV. Okay, N is the degree of variable, is the number of variables. D is the degree of the polynomial. Okay, so that we define the set IND as all exponent alpha. Okay, of any unvariate degree D polynomials. So there are totally SND elements in this set. And it can be generated as putting D balls into N bits, all possible choices. Okay. And based on the index, we can define the matrix DND as the xi power alpha D, alpha I power alpha D. So the alpha I power alpha D is the multiplication of alpha ki power alpha kg. This is scalar. This is power of 2 vector. Okay. So that's why we call it the power product matrix, because it's power with multiplication. Okay, and we can show that this matrix is here is the example. Okay, you can see that this is diagonally, this is the block matrix. Okay, an upper triangle, large triangular, and this is sparse and invertible. Okay, so here is the theory. So we can show that for any ND it's non-singular, it's sparse for particularly if a number of variables is larger than number of the degree of the polynomial, and the sparsity we can compute exactly by this formulation. And here the example, for example, once n, the number of variables increase for different d, for all kinds of d from 2 to 12, and if the number of variables is larger than 12 or 15, the sparsity is up to 90%. So it's a very sparse matrix, meaning that it can whose inverse can be computed very efficiently. Okay, and based on which we can construct this decomposition. We call it the term-wise power sum decomposition. So for even, here we separate into even and odd degree polynomial forms. For even degree polynomial forms, as polynomial P, we want to construct into a power sum of linear forms. And what we want is alpha is in the set and D, and the coefficients we want to compute it. And we can show that this is equivalent to solving this linear system. And you know the matrix D, whose inverse is invertible and whose inverse is very easy to compute it. So this decomposition can be constructed very efficiently. Okay, by solving this sparse linear system. And for the odd degree, it's also easy to be casted at the even degree by introducing an additional variable xn plus 1, because it's an even degree. In this case, we find the decomposition, set x1 equal to 1 to get the decomposition. Okay, so this is by combining both of them, you get decomposition for any polynomial. The second idea is homogenizing and dehomogenizing power sum decomposition. This meaning that instead of you get decomposition for form and forms, we can get decomposition for the whole polynomial by homogenizing first, because any polynomial can be casted into a homogenized polynomial by introducing in this form. Okay, by introducing xn plus 1 power d like this. And once we get decomposition, we can just set this variable to be 1 to dehomogenize. Okay, so just one step, homogenize and dehomogenize, you get the decomposition. So this is the second case. The detailed decomposition technique developed in this field. Okay, so right now we have a look at some numerical results. So here is a comparison of spectral decomposition and the parity decomposition and minimal basis one. And you can see that first, if the decomposition with convexity is more complicated. Okay, so the average time is larger than decomposition without convexity. That's the first thing. So if you need a more beautiful property like convexity, you should pay something. Okay, the average computing time is larger. The second is that among the decomposition with convexity, the minimal degree decomposition is the best one. Okay, so that is the best one with respect to the computing time and the variation of the degree. Okay, in average. And here is the speed up for 60 processors as well. So the 80 for the maximal speed up for improve the parity decomposition, and 12 for the maximal speed up for minimal degree one. Okay. And here is the performance of power sum decomposition. So here we compared with the D-SOS DC proposed by the paper in the paper of AAA, and we compare them with respect to the increase the size of the variable and the number of the degree of the polynomials, and we compare the computing time. Because they're different kind of technique, we cannot compare the quality of the decomposition. It's not the same decomposition, right? We can compare the computing time. And here for our method, we illustrate the generating time is to compute to generate the matrix D, and the solution time is to construct the polynomial decomposition. So you can say that the construction is always almost negligible. Okay, 0.something second, even a large size program. But the decomposition based on AAA is very sensitive to the scale. It's up to the 1,000 or 2,000. Okay, but we just several 0 or 2, the maximum in 50 seconds. Okay, but the generating time is sensitive. It is increased with most sensitive is about the degree of the variable, not the number of variables, but the degree of the polynomial. But it's not a problem in practice, because for if n and d fixed, the matrix is fixed. So you cannot generate the ones and store in the computer. You can just apply it. Okay, so to apply it is just a few seconds. Okay, so this is the advantage of this method. So that's what I want to say. I think it's about time I will just talk about some interesting open questions. So here, the first open question is about how to get a minimal degree decomposition with the shortest number of terms. Because of the, if we have some decomposition degrees minimized, it optimized, but the number of terms could be blow up. Okay, and in this case, to minimize if this decomposition serves as an objective function of some optimization problem, it's difficult. Of course, we can introduce some stochastic method, okay, to make a sampling and stochastic method to do it. But can we, in theorem, construct the theoretically guaranteed minimal degree and minimal terms decomposition? That's the open question. The second is the power sum type decomposition with, again, minimal term, because different types of bases leading to a different length. Okay, but can we get some, in theory, get some bases which will leading to a minimal number of squares again in power sum type? That's another question, because power sum type is very interesting. Good construction is very efficient. Okay, just solving a sparse linear system. The third one is undominated for DC-SOS. If we know that D-SOS is undominated, but DC, we still have no idea. But if undominated is very important. If it is undominated DC, meaning that there does not exist any better decomposition than the current one, okay, in the sense of domination. And this leading to her best approximation in DC algorithm. So leading to her less number of iterations. Okay, so that's an important question, three important questions in our current work. And I hope if you are interested in, we can have more discussions. And thank you for your attention. I will stop here.
Thanks, Professor Niu, for the excellent talk. If you have any question, please ask freely.
When you say some of the decomposition can be speed up by parallel computing, some are not.
Yeah.
So what's the reason why some of them cannot be speed up?
That's a very good question. So here I think, so for example, in the DC-SOS decomposition, we can see all cases can be speed up, right? But in D-SOS, you see, yes, there is one case in the PP D-SOS, it cannot be speed up. I think the important thing is that in PP decomposition, each process, whose computation is very less expensive. It means that it can be treated very quickly in this case. But in all other cases, each parallel processor gets a little bit more expensive computation. So in this case, we can have some speed up, but once each process do very quickly, the communication cost play a more important role. Okay. So we have not seen the speed up.
So it depends on the structure.
Depends on structure, yeah. Here we can do nothing because each term is just very quickly, and but we cannot do better. So here we cannot see this speed up, but others we can see, right?
Okay.
I think this is the most important reason.
Yeah.
Communication cost.
Yeah. Recently some people are working on how to speed up.
Yeah.
By GPU. Speed up the computation.
Yeah.
Whatever algorithm they want to do. And some people make a very naive claim that they speed up the algorithms, but actually not methodology sense. It's just from parallel computing sense. So it's just hardware or the implementation details. Sure. I'm not sure. I mean, that there's any improvement for the methodology. Anyway, so the next question is for different decomposition of the SOS. So you want to solve that by SDP, right?
I don't solve any.
You don't solve the SDP.
Yeah. But I compare them. It's not comparable. Here we are very quickly. SDP is very sensitive in scales.
So you don't solve any SDP.
Yeah, I don't solve any SDP. That's my idea. Because SDP in theory we know is equivalent, but in practice we never use it because we want to solve some large scale cases.
That's right. That's right. Okay. All right. Good. Thank you.
Thank you.
Any more questions? Okay, thanks, Professor New again.
Thank you. So maybe I copy you the slide, right? Okay.